Yeah, I know quiz. You got the format back. Previous. Second one, I do. He is Steve Martin. Quiz. Quiz. So why is the magnetic field equal to 0 outside the solenoid? The flux is so weak compared to the outside. I see. Because the flux unit per unit area is has like.
With the calculation last semester.
Hmm?
With the calculations, all of them last semester.
You can feel. So even outside, so how do you do it?
I don't remember, but I have the.
Find the magnetic field on the outside. All the fields will all cancel each other out when you do other loops on the outside.
We did the amperes loop and
So you can't prove mathematically, right? Can be, should be, otherwise you don't believe it, right? Can be, yeah. I was expecting that you can do this using some symmetric principle like Gauss's, sorry, Ampere's law. So that was mine. So, but is there a
the same
simple
thing
way?
as
Yeah,
symmetry.
again, try if you can do it using Ampere's law or not. Surely the actual long way is surely possible, but is it possible to do that? Is Pravina and Vilakshmi coming? Do you know? Yeah, they are coming. Actually, that office is right behind this. This wall, right? Isn't that?
So,
They can hear the lecture from. They can hear the lecture from the.
I think they are in a meeting in Dr. Shiva.
Ah, I see. Yeah. Okay, homework. 3. Homework 4 is expected that have posted before Thursday and it will due. Next Thursday. Yeah. Any comments or questions on anything? Yes, I think Manuka made a comment, I think that is good, for everyone, I suppose, I go over that. But any other thing that you can, you think might be useful to bring it up for everyone? Max, how is it going? It's so, okay, so slightly it might be different. Is it any different or you're familiar with all this?
I'm learning the notation, so. Okay. So it's okay, so that's good.
Ryan, you want to say something?
so for homework 3, we're just commenting on the first question.
Oh, yeah, that is just a, no, it's not a comment. To comment, it is a comment from my side to you.
Okay.
So you just don't, you just have to read it and be aware of it.
Ah,
Yeah. So it was just a, yeah, good point. When I say comment, it can be interpreted as please comment.
yeah.
Right, okay. Yeah, so there was this point brought out that how do you suppose you have a matrix M or a tensor, let's say it is A times B. And typically when you say M square, understanding is M. That's equal to A times B dotted A. That's it. This is vector A. Keep it intact. That should be straightforward. But once you have done this, you realize that this is a number, unless you're in quantum mechanics, where these are operators, these are, this is now a number. I can bring it out. A, B. Remember in a matrix, when you want to see this as a matrix form, AB is not the same as BA. Like the position of the vectors makes important, plays an important role. So 2 times the dyadic M is again a dyadic, or if you want a matrix times a matrix can be thought of as a new matrix, which whose coefficients now has changed. Right, so in a sense, this is again B dot A times A times B is M. It's the matrix itself, the product of the matrix is the product matrix itself. What about trace of M? The matrix? What is that equal to?
MII.
It is MII, so the main idea is that when you say this is a trace of the matrix, that you're looking for trace of this is A1, B1, A2, right, A1, B2, A1, B3, A2, B1, A3, B1, B2, B2. Trace is the sum of the diagonal elements, so I pick up all the sums, that's equal to A1, B1 plus A2, B2 plus A3. B3. That's equal to A dotted with B. Right. So trace of the dyadic M, if it can be written as two vectors, is equal to A dotted with B, or if this was just the matrix M, M1, 1, M2, 2 plus M2, 3, that's the same as M I, right? If you cannot distinguish, if you cannot break it into two vectors, that's not necessarily always true. So then there's M I. So that's in that sense, it is a dot product. So you can say this will be equal to trace of M times M itself. Remember, trace of a matrix is a number. Right, so you've got a number there, and now we have trace of M, so or the square of the matrix, if you want, is equal to, this is a number that comes out, that's equal to trace M times trace of M. So basically the trace of a matrix square is equal to the trace of the matrix square. But the main point is I'm not keen on this proof here. Main idea is the notations. Notice how the products go around, how the scalar product works in that. I didn't have to really use the fact that this can be written as a vector. If you use index notation, it goes through. But if you write it as a product of two vectors, you see the operations coming out plainly. Most importantly, when you say this times this, you cannot just write it as a square and just leave it alone, because the dot product then it's not clear where it sits in. So that's just a notational illustration of the notations we are using. So the dyadic notations that we are using may not be, everyone may not be very fluent. Okay. Any questions on that?
What is 2 times trace?
2 times trace.
Like taking the trace of trace. Does it make any difference?
Oh, I think then the question would be, so, for example, let's say trace of M, that's a number now, right? So that's a number. But what one could say is that so if I want to define trace again, the only way is that I need to put a 1, right? I need to put a matrix construction there. I need to have at least an identity matrix. And then probably you can say this. So probably that's your question. Right? Is, or you're asking, is trace of trace valid at all? But trace will be trace of a number. So then it is just a one-dimensional matrix. But if you put in an identity, then you're constructing a matrix out of it. And then you can say this will be trace of 1 times trace of n. Does that help? So that's already a number. Trace of the identity matrix is the dimension of the space or the rank of, I think you call it the rank of the matrix. Or whatever the number of the, like if it's 3 by 3, so it is n times. So n times n, I suppose. Is that clear? Yes. So yeah, open and so. Okay. So using these notations, we have been working on conservation principles, again, Maxwell equations. Our divergence of divergence of B is equal to rho, where D is equal to epsilon naught times E. Divergence of magnetic field is equal to 0, is equal to naught times H. And we have del cross E plus dt is equal to 0 del cross H minus J. Right, that's here. 4 Maxwell's equations. And also the Lorentz force. That's an independent statement. This is not, this cannot be deciphered from the Maxwell's equation. That's an independent statement in itself. And that is that I'm going to write it as a force density. Right, this is a local statement at every point in space and at every point in time. That's equal to rho times the electric field plus J times P. Right. That's if I integrate this over volume, I get force equal Q times electric field plus Q times V. This is a very specific scenario when the charge and current densities are for a point charge. So F here is integral. So that's so an integral. So force per unit volume or force density, if you want, is a small f. So that's your two laws that we are working with. This works for charges, this works for the fields, and the idea is how does one affect the other without the back reaction. So we're neglecting the back reactions. We made some, we deduced some conservation laws. One is conservation of charge. Charge density. The local statement will be E rho by dt plus divergence of J plus 0 is equal to 0. Why do I write that 0 there? What does that mean?
For the mechanism,
It's a,
for magnetic field.
no. Maybe, but that's not, there's another interpretation there. So that means there are no sources or sinks for the charge, right? Like in general, a continuity equation will have a change of charge density. This is the flux. Like think of the population of a country. That's the change in, that's the rate of change of population. This is the amount of population crossing the border. And this is the death or birth. And for charges, only for charges, there is no death. That means there is, the charges do not disappear, or they cannot be destroyed, or they cannot be created. So that's that statement, and that's that's a crucial implication of Maxwell's equations. Right away, you could have said that charges cannot be created or destroyed. Okay, and remember J is flux, right? So the J in this way is the flux of rho. So flux of charge, if you want. So that's a current, right? That's the idea of current. We then talked about conservation of no, what did I say? Conservation of energy, right? And that tells you that change in energy density, so say U small u plus. I use small u here, but in your homework, there's a good chance that it might be capital U, so be careful with whatever notation is being used. Maybe I'll keep the capital U, so this is capital U. I think in your homework, you use capital U, right here. So, plus, S plus J after the E is equal to 0. What's the interpretation of the third term again? Source or sink of energy. So how do you lose energy, electromagnetic energy? You can make the charges move, right? So you can convert that energy into motion, right? So this is the amount of energy lost in making the charges move. That means the field is no more there, the energy is no more stored in the field. Instead, it is stored in velocity. Right? So you converted that energy, and that's that. So it's called dissipation. How much energy is dissipated into some other form, most probably into motion. This is the flux. So S is a pointing vector, and we said it is E crossed with B. And that's the pointing vector. Or even better, this is a flux of U. And U is epsilon. Right, that's B dot with E. E dot with D plus H dot with B. That's equal to energy per unit volume. Or electromagnetic energy, EM energy per unit. Not any form of energy, only the electromagnetic energy, which is always shown in electric and magnetic. Here we want to talk about conservation of momentum, and then we will do applications.
Is it capital U or lowercase u? Energy or
In the last class, I think I did lowercase u, but in your homework, it was capital U. And I keep interchanging it.
I think you did capital last time.
In the last class, I did do capital, okay, so then I'm consistent with this capital U, so I think I started with small u. Probably because in introductory level physics, you use capital U for energy,
energy?
right?
For density, usually you use the
Small u, right? So I think it's the introductory level physics that I'm having confusions with because I should quote. But in this class, it is good to keep this u. I think let's stick with that. Feels pretty good stuff. And again, so now what we want to do here is, when we say momentum, so of course, this is energy conservation of energy density, right? So this is conservation of electromagnetic momentum density. So what we will have is, we will have dg, this will be momentum density, right, plus divergence of, what will this be equal to? Divergence of, will this be a scalar or a vector?
vector.
Okay.
Think again. This was a scalar. I had a vector.
So it's
It's a vector now.
So it's
tensor.
So it has to be a tensor, right? Because if it is a vector, after I take the divergence, I get a scalar. I cannot add a scalar to a vector. Right, I need to add a vector to a vector. So the only possibility there is that it must be a tensor. Because after I contract it with one of the vectors, I should get a vector remaining. So the expectation is that this will be a tensor. That's what we will try to see. I haven't told you what these things are. This will be T and plus whatever remains will be interpreted as a force density. So the question is, can we write, starting from Maxwell's equations, can we construct something like a momentum density of the fields? And we construct a flux of momentum density, and remaining can be interpreted as a force. So what we will do is, we'll start with the Lorentz force. Like last time we started with the power equation. Power was rate of change of energy. And we got this, that was how we started with, right? Energy, rate of change of energy per unit time, that's how we got that same thing. We'll start with the force equation and see how this goes by. Okay, so the question is, what is G? What is P? And what is that? The force is actually, okay. Any questions at this point? And then we will do the very first example will be, suppose you just take a plate or we take two parallel, yeah, so this is how we'll apply this. Suppose you have two plates. Let's say positively charged plate. This is infinite extent. And electric field then will be like this. If you have two parallel plates, what's the magnetic field inside it? Two charged parallel plates.
Sigma over epsilon.
Magnetic field.
Magnetic.
Yeah, magnetic field will be zero, right? Electric field is sigma over epsilon, correct, right? So electric field is equal to, if it is conducting plates, it is sigma over epsilon naught. That's a vector, z hat, and let's say that's a distance a, right? So only for a z less than a and greater than 0, it survives. Everywhere else, it is 0. So here is a question for you guys. What is the force on the right plate due to the left plate?
that QE.
Yeah, so
Yeah.
Q times E, that's how you calculate. What will you get? So you should get force, you should try force per unit area maybe, right? So let's do 4 because otherwise it will be infinity. So try force per unit area. And say do some integral, so divided by area. So what is that going to be equal to?
Sigma squared over epsilon.
Sigma square over epsilon. U. And probably a z hat. Is that correct? We never asked this in introductory level physics. So the answer is wrong actually. And to do it using this method, yes. Okay. We will do this using a different method at the end of the lecture. And we will see that this is missing a factor of R. Okay, but intuitively, yeah, why not? Right? Remember that if you have an electric field, like this is that there's a conceptual issue here. If you have an electric field and there is a positive charge, what's the force? That's Q times E, right? Here, the electric field comes to an end there. It's not in an electric field, it's like this is the, like, it is all sort of, and this is sort of contributing to the electric field itself. Like these charges are necessary for the electric field and there. So, and so often you argue that, oh, this is an averaging there, but one has to do this more carefully. So one has to ask.
Can you say because one plate is half of this?
That's the typical argument, but that's hand waving. If you didn't know the answer,
Yeah.
you wouldn't guess that, right? So I think that is hand waving it off. So try to come up with a good answer. I think it will lead to a lot of conceptual understanding if you try to derive this using some method. No, it is not trivial. Often it is as a balancing act here to do. That is.
Wait, so what do you want us to do for the quiz?
Find the correct answer. This is a
Oh,
wrong
right.
answer, right? So, well, that's something missing. There's a number missing here, and I'm telling you, it's half.
Yeah.
Half is the factor. So try to derive that using your favorite method. Use any method you can and get that. And I expect that if you're not careful, you will mess up. Okay, but we are going to use machinery, new machinery for doing that. And we will first develop that machinery. So let's start with force density is rho times the electric field plus J dotted with the magnetic field. Did I write across that? Yeah. Introduce Maxwell's equation. Rho is L dotted with D, and then you have an electric field plus J is del crossed with H and minus E over dt crossed with B. And this is the force on the electric charges and electric currents. But we can pretend that there are magnetic charges and magnetic currents. If they're not there, it is zero. So this is the 0 plus 0. Many reasons for the zeros. So this is one of, like this was what we were suggesting about that, yeah, electric. There are no magnetic charges. So then you would say this is rho times H And you would say that's del started with B, which is 0, times H. That's a 0 I have added, that's perfectly okay, but that is to manipulate the equation, have the construction clear. And plus 0 do the same thing, but then I have a choice, right? Is it a plus or a minus? So I'll write this as del minus del cross E minus dP by dt. And cross with oh, did I do this correct? Cross with B, so this will be cross with B.
And you just take out the negative sign.
I can, yes, you can take out the negative sign. Yes, why not? Like that. Reasonable? Oh, then I have to cross. Yeah, but it's a 0. I can put a negative or a positive, and the idea is to build something which really comes out as a dialectic here and interpret the okay. Okay, so let's get the time derivative first. I have time derivatives, 2 time derivatives. Take it in to the left. So I have f when it goes to the left, it becomes plus by ct cross with t, and that is plus. Oh, I don't think I want to do that. I will add actually. Because I want to add. I had a choice of adding or subtracting. I want to add because I want to put this together, right? This is B cross B. Right, I want it as B cross B, right? So that the derivative goes through. So that was the idea. So that is the
So then yes, put a negative sign.
that will be negative sign. Thank you. So this will be dB by dt cross with B. Like in this way, I can actually take the derivative out because if I flip this B cross B, then that's the same point. Right? So there's a distribution property in that. I should rethink my plus or minus here also, but I'll know very soon. Let's see, now there are 4 pieces in here. So it's minus. Let me keep it on the right side. Why not? So no. B times electric field plus del cross with H cross with B. And this is the same piece, right? Except no, I want to write this one first. Del cross. Okay, so this is both magnetic fields. So let me write the del cross with E cross with B. And that is a magnetic field also. Plus. H and these two are pretty much identical. No, what is that answer? These two are pretty much identical. If I replace E with H and D with B, I can get from here to there. At least mathematically speaking, that's the same. This one I immediately write F plus time derivative of D crossed with B. That's a distribution. First, use the negative sign to flip the position of this, write this as d crossed with d by dt, and then you see that this is a distribution of the time derivative, and you get the time derivative of some quantity. That's the idea of this G, right? That's the momentum density. That's how we are going to interpret that. But the continuity equation works only if you can identify this as a divergence. Okay, so you want to take this divergence out, and that's what we want to investigate here. So let me do this separately here. So let's work with. Idea is that this can be returned as a divergence. So let's see if I can do this. So del cross E cross with D. This is minus of D crossed with L cross E. Then it is A cross B cross C. So this is gotta keep the positions intact. So this is a divergence that has to still act on E. So this is D dotted. Remember A cross B cross C is equal to back cap, right? So this is B, A dotted with C. But if I'm not allowed to move A and C around, I cannot move C around because B has to still act on. Like the gradient has to act on E. So I cannot move this out or take this A in. So I keep this intact and keep it in mind that this is dot. Very, very crude way of writing that, but that's fine. Retention. So that's minus of cab is easy. A dotted with B. And then there is C. I can move this around if I do the following. That's notice this is the only operator here, right? That's the gradient. That's what is important. So I can put this in front. So dotted with A. Here the notation is that first I have to operate B on C and then dotted with A. All this gymnastics you have to do primarily because this is an operator. Okay. So I'm going to do that here. So this is the back cap. So the same thing here. This is dotted, but I can move this onto the right. So this is minus and a plus cap. So this is E is the free. This is D dotted with times E. And I'm going to do this as first operate this without the it being a scalar or a vector, dotted with D plus. Is that clear? That should be bothering. If you're not familiar with the notation, this is this challenge we will come up again and again, the gradient sitting in there, and you being here having to cross that. And this is a trick we will do to do that. Okay. Is that clear? Any questions? This will be a crucial step. So often we will stop writing this intermediate step because of that awkwardness of writing that arrow in there. So we just directly write that here, and then it shouldn't be surprised that what happened in between. Let's put in the epsilon naught so that you see the symmetry in this equation, and that is going to be done by, so this is minus epsilon naught times del of E times started with E. Plus epsilon naught times E started with we had this term also in here, remember? So we should bring that in. So we are interested in evaluating the whole quantity. So tau cross E cross D plus tau dot D dot with E is equal to put this all in. This is minus epsilon naught E plus epsilon naught E dotted with gradient E, and there's a plus epsilon naught, there's a del dotted with E times let's see that what could this be coming from. So let's think of the dotted with E plus E times E, and it might be negative. What is wrong in this equation that I wrote?
Scalar and then.
Very good, right? Very good. One is a scalar, one is a tensor, so you cannot do that. To make this a tensor, so very good. Okay. So that's a notational, that's the first thing that should come in the notation that you should realize. Let's see what this is equal to, and if that is the case, then let me also operate this with, if it's a tensor now, I can operate this with this quantity here. Remember, these are all epsilons, I can bring it out, and I want to see if this is anywhere close to what we have here. So epsilon comes out, so I have epsilon naught. So this is this is simply del itself. When it acts on one, it is just gradient itself, but it can also hit on D, right? So this is equal to divergence of the E dotted with E. So it's E dotted with E, because one and one vector multiplied with that unit direct is one, and this one I can act on whichever I want to. So this is epsilon times del dotted with D times E multiplied by E, and next one is when this is this vector is going to hit on that. that is minus of epsilon naught times E dotted with divergence. If you notice, hopefully these pieces all come together. Let's see. Let me write this one more step. This is epsilon naught. Divergence of E. Change the parentheses to emphasize the difference. Right, that's now looks like this. Next piece I want to see is this one. So it's minus epsilon naught E dotted with E, so that's this piece. And the last one is, did I get science correct or overall science of it? So that's so overall, this seems to be equal to, if this is the same as this, that's minus, right? So that's minus of del. Sorry, minus of the whole quantity. So this is minus of del cross the sorry, minus del. And our goal, remember, was to recognize some, is there some divergence? I'm just interested in the divergence. If there is a divergence, then immediately that means that there is a conservation equation, there is a flux of the momentum, right? So the idea is to get it in this form. And it seems like there is, because now this is the same as this. So I bring it to the left. So notice this is all this is onto the right. When I bring this, there is a negative. So this is the same as plus del dotted with the whole quantity. So that is 1 times d dotted with E. Did I miss something?
The last
Did I
line,
say
the
something?
first
Am I
one,
missing something?
they can turn, don't they cancel out?
First and the second term.
The last line,
This one and this,
the first and second.
first and second. No, right? Because this is not an E is dotted with E here. And here E is dotted with this gradient. Right, so it does, so it's a different operation. So here, the meaning, like this has a good meaning. This is the derivative of this field in the direction of E. So this is called a directional derivative. So that's a useful concept to keep in general. We won't be using that too much, but if you have a feel for that, that's good. And this is just a derivative of every component. Like this is the complete tensor derivative, like this is all the derivative, like x with x component, x with y component, x with z component, all derivatives are sitting in there.
Aren't aren't the second and third term technically the same since that for dot product the order didn't matter?
This is the order, dot product, the order doesn't matter, but if there is a gradient, it matters. Notice the notation, this is operating on E. Right, and then you take the dot product with E. Here you're taking the
Dot product.
operation and the dot product of one, and this is just sitting there.
Okay.
But there is a mistake in this. I did make a mistake, and that is here, right? So this one, correct? This one is supposed to act on both the electric fields. Right, when I wrote this, I acted only on the first one. Correct? But these are both electric fields and it's a dot product. So there's a symmetry in that if I were to act on the next one, so the next piece here will be E dotted with, so there is a del dotted with E, so remember E, and then you're like, if you want, this is an action in this direction. Is that clear? What I mean there? Like I have to act on this electric field. What I can do is first interchange. So this is how about it? Maybe write it like this: E dotted with E. For a moment, let's say this is 1 and 2. They're the same, but this is just to recognize the fact that they are separated, right? So this is equal to del of E1 dotted with E2. When I want to do the second term, I first move this around. It doesn't matter to it is commute. So then I say it is del of E2 dotted with E1. But these two are the same because E1 and E2 were just an artifact. Like I just constructed them. So those two are exactly the same. So this is not really equal to this. This is equal to 2 times that. Right. So this is equal to 2 times that. So I need a 2 in that. Right. Or since now this will not match this, so what I do is that, I want to put a half there. So when I start, I begin with a half, so that this will be a half in there, and this will exactly balance out there. Like I need that if I want to get this, which is what my equation has. Okay, I should have been more careful in putting that. But that's also a part of energy. That also makes sense. Why did you put it on? Because that although I'll get this 2, right? This is equal to 2 times del E dotted with E. If I don't put this half there, I'll get a factor of 2 here or here, right? This will not match with this. This will not match with what I'm interested in. So if I'm interested in this, I want to start with a factor of half so that it balances out and gives me exactly the left hand side. Okay. Clear? Yeah. Good. Okay, if that's the case, then there's a half here. That's all. And there is also a piece from here, right? This is exactly going to go the same way. That is a plus part of B dotted with H. And minus of B times E minus of B times H. And this whole thing is equal to 0 because I've moved it out to the left. This is wrong. Clutter? The thing. So I have recognized my flux if you want. So our definition will be G will be equal to D crossed with E. It will be electromagnetic momentum density. And T is equal to whatever we had there, but you recognize that the first term, what is this equal to? That's already my energy density. except I had to multiply by 1. Right, because I had to make it a diagonal. So it is energy density times a unit diadic times a diadic construction of the electric field and E dotted or D times H. So what will this be equal to? So this is the flux of momentum. When you say, for example, think of a wave, we often say that an ocean wave, when it is moving, all the particles are moving up and down. Like in an ocean wave, all the particles are going up and down. But the force is exerted in the direction of its motion. If you stand on in the motion of an ocean wave, it can come and really hit you hard. It can hurt you, right? There is a lot of momentum in that, even though everything is going up and down, the momentum is in the direction of propagation. Right? So that's that momentum. So that's the flux of the momentum, right? A non-trivial concept in a sense. Yeah, and here it's not even particles moving, it's abstract quantities, electric and magnetic fields that's changing that stream. Exerted force. So whenever we want to calculate a force, in principle, we can do this. Right? So we always think of it in terms of charges, like if I want to find the force on a positive charge in the presence of an electric field, you will do Q times E, but we can do this now, and in principle, we should get this. So let's do the force on one plate of a parallel plate capacitor, right? We should get force on that. Let's any questions on this algebra?
So if we do this part,
Mhm.
you can find answers for the like
For this,
yeah.
that means that this is equal to this.
Yeah, so did we come to that point using this like the last part? Yeah.
Yeah, because I reached till here.
Okay.
From this to the next step, I used this,
Okay.
right? Like it was just my inability that if if you were careful, you should have gone 2 more steps.
So we want
And you would have gone it the other way.
right?
Yeah, so you would have met it there. So instead, I came from both sides.
Okay.
So that was not the most elegant way of doing it. Does that help? Yeah. Yeah. Okay, so. Any other questions in the algebra? Okay. So we are again in the problem of a capacitor. So we have a positive charge plate, negative charge plate. That's your electric field. And these are infinite electric field is equal to, let's say that's your Z direction. Hat times sigma over epsilon, right? Sigma is charge per unit area. The total charge will be infinity, area is also infinity, sigma is fine. And we want this only for Z less than A, greater than 0, it's equal to 0 otherwise. So that's all the electric field between the parallel places. What about the magnetic field? That's equal to 0. So G, what is G equal to? G is B crossed with B. Is equal to 0 everywhere, right? That's no doubt. And that's one of the term we did immediately. But now we want to calculate the force. So what we can do is that force density is evaluated at a point is equal to minus del divided with T and minus dg by dt. This is equal to 0 because g is equal to 0. So there is no change in the momentum density, so there is no contribution from the changing part of the momentum density. So it has to be because of the flux of our momentum. So first we have to decide, I'm doing force on what, right? I'm interested in force on, let's say, one of the plates. So I'm going to evaluate the force on this. So I have to specify a volume. So I'm going to calculate the force on this whole plate. So that's a volume I create, and I'm going to extend that to infinity again. So I've created a volume which is almost snugging with the plates. So this is a volume I have created. Right, that's a volume. Okay, is that clear? So the force on the plate would be equal to the volume integral dq r on that shaded region. That means the shaded region in the figure, right? Times the force density. Is that clear? Force on every tiny piece keeps adding on, right? And I get that. This can be thought of as an area times a dz. Okay, so this is equal to, so this implies that force per unit area will be equal to dz, where I have to go from 0 minus delta to 0 plus delta dz times f. Is that clear? So when I'm saying I'm integrating this plate is 0 minus delta, this plate is 0 plus delta. Remember, this is z equal to 0, that's z equal to a, right? Z equal to 0. A. Is that clear, the construction? Any? Yes. Right.
For G equals D cross B, isn't it G equals D cross E?
Was it E? No, I think I meant B. If you go back into your notes, I think I wrote it wrong here. This is B. Sorry. Look into your notes.
Oh, yeah.
Right. I think I said it wrong. My bad. If the correct this, it is D cross B, not D cross E. Okay. Sorry about that. This is 0 then. Good catch. So that helped me point it out. And now force is equal to the integral of force density over the volume. But volume is mostly along the z direction. That is the whole infinite area. So I'd say force per unit area, right? For the plates, that's what we talk about. Okay. So
They're creating like plus delta and minus delta from the shaded.
so we are snugging the plate, right? We need to create a volume. I can make it as much as I want. It doesn't really matter.
That symbol means the shaded area, right?
Yes, this symbol means shaded area. Yeah.
In other interval, the next one.
Oh, here.
Yeah, what is this?
Yeah, so this is the 0 minus delta. So here, this is the volume, right?
Okay.
This is the volume. Shaded volume, if you want. I have pulled out the area. So whatever is remaining now is only z. So now I can specifically say how much is my z. So this is equal to z equal to 0 minus delta. Maybe that helps.
Yeah.
Wouldn't it, wouldn't the volume just be from 0 to 0 minus delta?
And that's because, very good, that's correct. That's because probably you're saying that there is no field in there. or make, if not, okay, so this is my plate, positively charged plate. Okay. And remember, this could be a material, right? So this could be a metal. Right? This is a metal. That's how we construct the capacitor. But I don't mind that. So this is my volume. And let me say this position is Z equal to 0 minus delta. And this position is Z equal to 0 plus delta. This is inside of the metal.
What is the other line?
This is an abstract volume.
No, what is the other line supposed to represent?
Oh, this one is my volume. I am going to calculate the force on a volume, an abstract volume, right? Then I can come back and put it as close as I want and calculate how much it is or what, because I'll capture those charges. I'm interested in the force on these charges. In a metal, the charges are always on the surface of a metal, correct? So if I capture that region, that's sufficient. Is that clear? Okay. That logical process is necessary. Good with me? So then force per unit area, that's what we are going to calculate, is equal to, this is the Z. Maybe I did this too early. Keep it back. Right, keep it back, and our volume isn't necessary. No, why not? It can always be done, hopefully. The Z 0 minus delta, 0 plus delta, force is minus delta T. Right, so it's minus of del dotted with T. This is an infinite area. I expect the force to be in the Z direction. Right, so let me take the Z component of the force. So let me do F dotted with Z, and just to get this clear, let me do that from the left and no. Oh. This is a I want to use the divergence theorem somehow. Yeah. Okay. Hopefully, bring the area in. Bring the area in. That's a volume integral. Then you take a surface integral, and you want to say that this is 0 minus delta dz. No. Help me. Sorry. Okay, why am I struggling? Okay, force is equal to volume integral again. So this is volume integral dqr of del dotted with T. There should be no doubt about that. But that's clear. I'm going back in this step. Use your divergence theorem, make this an area. This is now, so this is the volume now you're talking about is this, right? This is the surface enclosing that volume. So it's only the side, right and left, right? So this is a closed integral, and that's dA dotted with T. This will have two surfaces primarily. Right? One is on that side, one is on this side. So this is equal to minus of A. When I'm on the left, it is minus Z hat dotted with T. Evaluated at Z equal to 0 minus delta. Because it's evaluated on a surface, right? Plus, now minus again, area times this is plus Z hat dotted with T. And evaluated at z equal to 0 plus delta. Is that clear? Did I confuse? Okay. Few minutes closed. Very quickly. I'll finish. Okay. So force per unit area is equal to plus and a minus. This is plus z dotted with t. And this is minus the half dotted with t. But this is evaluated at 0 minus delta. This is evaluated at 0 plus delta. The first term, what is that first term equal to? Quickly.
Easy.
Yeah, but there's a simpler answer. Use conceptual. You're thinking the algebraic way, that's correct. But I'm saying go further. What is easy?
The projection.
This is a conductor. Inside a conductor, what's the electric field? Zero, right? So it doesn't matter what I do, electric field is inside the capacitor. Outside the capacitor is zero. Right? So this is outside. I don't care what it is, electric field is zero, magnetic field is anyway zero everywhere. Right? So this is zero everywhere. So I get, of course, you guys all said that you don't have anything after this, so fine.
Yeah.
Right, so sorry for that. So it's minus the hat dotted with t. You guys have something?
I've got a meeting at 2.
Two, I'll finish that before. Give me. It's 4:54. Okay, let me not talk. Let me take the z component just for simplification. Z component of the force, so that's equal to minus z hat dotted with t. Remember, these are two indices, right? So I can take the dot product on both sides. And now you just put this in. Z hat dotted with t was equal to 1 times u minus of d times e and minus b times h dotted with z hat. Right, so that's 0. So this is equal to minus z hat dotted with 1 dotted with z hat u plus z hat dotted with epsilon naught times e and e dotted with c hat. U also, so this is all 1, so that's minus u plus epsilon naught ez squared. Go back to u, how much that is? 1/2 epsilon naught times electric field is all in the z direction anyway. So that's sigma over epsilon naught square and it is plus epsilon naught sigma over epsilon naught square and it is plus half epsilon naught sigma over epsilon naught square. And that's the factor of half that you see in there, which I promised earlier. And otherwise, this is the charge times the electric field. So you do charge density times the electric field. But go through these steps. This is mostly, I mean, conceptually, this is clear, but so think of this as a radiation pressure. Right? This is, we always think of it as a force on a charge. But this way of looking at it is, this is the stress due to the electric field coming and hitting on the plates. This is radiation pressure. I'll stop here. And the good point here is that if you had thought of this, I mean, you don't need the negative charges. Even if it was a single plate, you can think of a force. Always, the idea of a force requires the other charge, right? In this, just you have an electric field and you can, electric field can push, that's the idea. Like radiation pressure is the idea that just electric field can do work, do mechanical work. Quiz, last one outside the quiz is if you have a charged sphere, just one charged sphere, all these charges will repel each other. So the pressure on it. Calculate the pressure. Maybe.
It's solid or hollow?
Let's say make it hollow so that it will be easy. This solid also, but make it hollow sphere. They will all repel each other. Try to calculate the pressure on it. And you will encounter a problem because very close by, they are so close that it should be infinity.
You mean the pressure on all the surface charge?
On all the surface. So if the charges are kept on a conducting sphere, they don't like each other. So they'll try to push apart. And if so, that's basically a pressure, right? It's called the electromagnetic pressure. And we'll calculate that next lecture, but give it a thought on it. I'm not asking, or how about, don't calculate it. Just give a thought on it. How would you proceed doing it? But now that you have the machinery, you will actually solve the problem and get it. That's all. Thank you. You should run. I can do this if you want.
Can I-
Did you shut it down? Okay.
No, no.
No, not it.